Hello everyone, this is Yang from National University of Defense Technology. Today I would like to introduce my paper, SSP, Speeding Up Small Flows for Proactive Transport in Data Centers. Professor Dong and Professor Liu are my instructors. Professor Dong is a corresponding author. Shan Huang and Ze Jia also contribute to this work. So let's start with the background. Nowadays, a large body of applications such as web search and social networking place strict latency on the underlying data center. So over the past decades, the link speed has grown up from 10 Gbps to 100 Gbps. And as we know, network transports in DCNs can be classified in two kinds, the proactive transport and the reactive transports. Reactive transports are common to current DCN, and they deal with the network congestion after congestion arises. However, as the network transfer are completing faster in the field entities, reactive congestion control algorithms converge slowly and lead to poor performance. Reactive schemes only react congestion signals. For example, DCTCP. DCTCP used ECN to detect the network congestions and timely use RTT to detect. These reactive protocols need multiple rounds to converge to the correct sending rate. Thus, proactive transports such as Expresspass, NDP, and Homa are drawing attention recently. In the proactive transports, nHost use credits to schedule data packets. Here we introduce Expresspass briefly. This is an overview of the Expresspass. Receiver use credits to control the sending rate and schedule the arrival of the packets. As we can see in this figure, the blue squares are the data packets and the orange ones are representing credits. Suppose there are two flows from the sender to the receiver 1 and receiver 2. Firstly, the sender needs to send a credit request back to the receiver, and after receiving the credit request packet, both receiver 1 and receiver 2 start to send credits to the sender. And the credits are A1, A2, B1, B2 in this picture. Then the credits A1, A2, B1, B2 will experience a process called rate limit in the switch. In this process, switch will limit the rate of the credits and ensure making full use of the reserved link capacity without large queue buildup. As we can see, half of the credits from each flow will be dropped directly in the switch. And after receiving credits, the sender can now send the data packets to the receiver and now credits corresponding to one data packet strictly. Based on this algorithm, Expresspass can actively avoid the network congestion before it happens. So, compared to the reactive algorithm, proactive transport has many advantages. For example, bounded queue, fast convergence, zero loss, high utilization. However, proactive transports like Expresspass also have their disadvantages, that is, wasting bandwidth of the first RTT. Let's pay attention to the left figure. This figure describes the behavior of the nHost when sending data packets on the Expresspass schemes. Firstly, sender must generate a credit request and send it to the receiver once a new flow arrives. After receiving the credit request, the receiver sends credits to the sender, and then only when the sender gets the credits from the receiver, packets would be allowed to inject into the network. Now, from this process, we can see that the proactive transport need one RTT to send the credit request and get its response. During this RTT, the sender are forbidden to send any data packets. Obviously, this would lead one extra additive waste. So we did an experiment on ONNET to prove this. We measured the average FCT of 1 to 100 KB small flows with 3 realistic workloads, including cache follower, web server, and data mining on the Expresspass. And this is the result. We can see that on the 1 Gbps network, the average FCT of 1 to 100 KB small flows is around 7.8 to 17.8 RTT. However, when the link speed is 100 Gbps, the average FCT has dropped to 2.2 RTTs. So this indicates that if we waste 1 RTT, it equals to extend the FCT of small flows by up to 46%. Now we can know the first RTT wasted by the proactive transport is very important in DCN, especially for small flows. Thus, we need to avoid the 1 RTT waste. And so, there are some solutions trying to solve the waste problem. For example, Homa and pHost let new flows send unscheduled packet blindly in the first RTT. This scheme can avoid the first RTT waste, but it also brings to another problem. The unscheduled packet sent within the first RTT may cause large queue buildups and excessive packet loss. Then, according to the mechanism of Aeolus, unscheduled packets which are sent in the first RTT will be selectively dropped when the queue buildup occurs in the switch. Aeolus solved the congestion problem by dropping unscheduled packets. However, unscheduled packets are the packets sent in the first RTT, and as we described before, the average FCT of small flows under the 100 Gbps network is about 2.2 RTT. So this means that a considerable part of the small flows will be sent within 1 RTT. Thus, dropping unscheduled packet will greatly increase the FCT of small flows, resulting in an increase in average FCT of all flows. So about this, we propose SSP with two key ideas. On the one hand, SSP avoids the waste of the bandwidth in the first RTT on the proactive algorithm without hurting the performance of the small flows. On the other hand, to achieve better performance, we also use the method of flow scheduling to make sure that the small flows will be transmitted in the network first. Our design of SSP mainly includes three aspects. Firstly, we let all the new flows start at the line rate in the first RTT. As we can see in the right figure, the red line represents the unscheduled packets. Once a new flow arrives, it sends unscheduled packet at line rate during the credit request phase. That is the first RTT. And once the sender gets its credits, the fast start phase stops, and the sender would adjust the sending rate according to the receiver credits. However, injecting unscheduled packet may cause congestion in the network. Since low buffer occupancy is one of the main features of the proactive transport, we need to solve the congestion problem. Thus, in SSP, when the switch starts queuing, we selectively drop data packets which will enter the switch queue to keep low buffer occupancy. In particular, we drop scheduled packets once network congestion occurs and protect the unscheduled packets. Suppose the queue length of this switch queue has already reached the dropping threshold. Then an unscheduled packet came, we keep it in the queue. Then a scheduled packet came. Since the congestion is already occurs, we drop the scheduled packets. The reason why we don't choose to drop the unscheduled packet is because, as we described before, the unscheduled packets are more likely belong to small flows. Dropping them will increase the FCT of small flows, so we choose to protect them. To achieve better performance of small flows, we also use flow control mechanism based on short job first principle. We think both Expresspass and Aeolus ignore the short job first principle. We give packets different priorities according to the number of the packets that the flow has sent based on SGF principle. The more packets sent by the single flow, the lower priority will be given to the packets of this flow because it is more likely belong to long flows. Here are two flows ready to send. Suppose flow A is a small flow and flow B is a long flow larger than 100 kb. According to short job first principle, if the flow has sent more than 100 kb data, the rest packets of this flow will be given lower priority at the sender, and then all these packets are pushed into different priority queues respectively in the switch. When the link is idle, the packets from the highest non-empty priority queues will be transmitted first. And now let's talk about the implement. The first challenge is how to implement the selectively dropping algorithm in the switch. About this, Aeolus had an interesting observation. Aeolus found when the queue length of the switch reaches ECN threshold, if the coming packet is ECN incapable, then it will be dropped. If the coming packet is ECN capable, it will be kept. So we give different dropping priorities to the scheduled packets and unscheduled packets at the sender. Packets sent in the first additive will be marked with ECT1 as a lower dropping priority, and other packets are marked with ECT0 as the higher dropping priority. And also in switch, we set the ECN threshold as the dropping threshold. Switch can distinguish the ECN value carried in the packet header. So when the network congestion happens, scheduled packet will be dropped to avoid large queue buildup. In contrast, only when the buffer overflows, packets with high priority labels can be discarded. This mechanism can ensure low buffer occupancy and keep small flows packets in the switch as much as possible. In SSP, we also use flow scheduling to improve the performance of small flows. To realize this, at the end host, we give different priorities to the data packets based on the short job first principle by giving them different DSCP values. Then, at the switch, packets with different priorities tags will be classified into different priority queues. When a link is idle, packets from the highest non-empty priority queue are transmitted when the packets from low priority queues will be waiting. We use OMNet simulator and ANET framework in our evaluation. All the flows in our experiments are generated with 4 realistic workloads: web server, cache follow, web search, and data mining. We use a leaf spine topology that consists of 4 span switches, 24 leaf switches, and 240 nodes. The switches are employed ECMP to ensure path symmetry. This 4 figures shows the FCT distributions with a target load of 1.6 under 4 realistic workloads. First, about 63%, 50%, 72%, and 80% of the small flows are completed in the first additive for the 4 realistic workloads. It shows that SSP can avoid the waste of the spare bandwidth in the extra additive, which are required in the proactive transports. Also, we can see with SSP, better tail FCT are achieved for small flows. These figures are about the average and the max queue occupancy under Aeolus, SSP, and Expresspass with 2 realistic workloads, cache follower and web search. The results show that the buffer occupiers are quite small on all the 3 algorithms. As the load increases from 1.2 and 1.28, we also find all the 3 schemes max queues maintain a small value stably. This indicates that SSP can speed up small flows and meanwhile keep low buffer occupancy as Aeolus and we also measured the tail FCT of small flows. These two figures are the tail FCT of small flows under catch-follower workload and with different target load. We find, compared with Expresspass, SSP can improve the FCT of small flows by 35% to 56% at the 99th percentile, and by 14% to 36% at the 99.9 percentile. Also, SSP can achieve better performance than Aeolus. The results once again prove SSP can improve the performance of small flow significantly. In conclusion, SSP solves the one RTT waste problem of proactive transports, and we implement the selectively dropping schemes in the switch to avoid the large queue buildup and protect the unscheduled packets. We also give higher priorities to the small flows in SSP to achieve better performance. The evaluation shows that SSP can speed up small flows significantly and also can improve the FCT of small flows without any change of the hardware.